Right now, in an office in California, an 84-year-old physicist is quietly taking apart the theory he spent half a century building. His name is Leonard Susskind. He is one of the fathers of string theory, the framework that has ruled fundamental physics for 2 generations. And in a candid interview, he said what almost no one in his position has ever said out loud. String theory, in its precise form, is not the real world we live in, and he can say so with absolute certainty. We live, he says, in the wrong kind of world. Behind that admission lie 3 cracks. The theory requires a symmetry our universe refuses to have. Its equations describe 10 to the 500 possible universes, and cannot find ours. And its exact mathematics works only in a kind of space that is almost the perfect opposite of the one holding you tonight. There is a crisis in string theory, and by the end of tonight, you will know exactly why it is worse than you think. Before we begin, if questions this large are how you like to end the day, a quiet like or subscribe truly helps me keep making these. It costs you a moment, and it means more than you know. Now, let's begin. Every scientific revolution begins with a sentence someone was not supposed to say. This one was said quietly, in an ordinary interview, by a man in his 80s, and it may be the most consequential sentence spoken about physics in our lifetime. The sentence is this: I can tell you with absolute certainty that it is not the real world that we live in. The theory he was talking about is string theory, and the man who said it is not a critic of string theory, not a rival, not an outsider with a grudge. He is one of the people who invented it. His name is Leonard Susskind. He was born in 1940 in the South Bronx, the son of a plumber. He worked as a plumber himself, fixing pipes in New York boiler rooms, before he talked his way into an engineering program at City College, and from there into physics, and from there into a doctorate at Cornell in 1965. Since 1979, he has been a professor of theoretical physics at Stanford University, where he holds one of the most prestigious chairs in American physics. If you have ever heard the phrase, the holographic principle, that is his, developed with the Dutch Nobel laureate Gerard Hooft. If you have ever heard that black holes do not destroy information, that result came out of a decades-long argument Susskind fought with Stephen Hawking, an argument Susskind called the Black Hole War, and which, by nearly universal agreement, Susskind won. And in 1969 and 1970, working independently, and at almost the same moment as 2 other physicists on 2 other continents, he was one of the 3 people who first looked inside a mysterious formula describing colliding subatomic particles, and saw something no one had seen before: a vibrating string. For more than half a century, Leonard Susskind has been one of string theory's principal architects, one of its most creative minds, and one of its most effective defenders, which is why the interview at the center of tonight's story is so remarkable, because in it, calmly, without drama, without anyone forcing the words out of him, he said the things that the rest of his field has spent decades not saying out loud. He said that string theory, in its precise mathematical form, is certainly not a description of the universe we live in. Not probably, not maybe. His words were, I can tell you with absolute certainty. He said that the kind of universe string theory's exact mathematics knows how to describe is almost the exact opposite of the kind of universe we actually inhabit. His phrase for it, and remember this phrase because we are going to return to it more than once tonight, was this: we live in the wrong kind of world. He said, of the path forward, we have to start over again. Not adjust, not refine, start over. He noted, almost as an aside, a strange fact about the theory's 58-year history. Mathematicians have won some of the highest honors in mathematics, Fields Medals, for work growing out of string theory. But no physicist has ever won a big prize for string theory. Think about what that means. The most celebrated theory in fundamental physics, the one that has dominated the field for 2 generations, has been decorated in the world of pure mathematics and never once in the world of experiment, measurement, and physical reality. And then he said the thing that turns this from a technical problem into a human one. He said that the work of starting over, of building the theory that actually describes our universe, is barely being attempted. That when he asks young physicists why they will not enter what he calls virgin territory, open territory where anything you manage to say will be new, they tell him it is too hard, and then they tell him the real reason. He said, they're scared. They're scared they might not get a job. An 84-year-old founder of the dominant theory of fundamental physics, telling the world that the theory does not describe reality, that the field must start over, and that the next generation is too frightened for their careers to try. That is not a small story. That is arguably the biggest story in physics, and it is being told almost nowhere. Now, before we go any further, we need to be careful, because this story is easy to get wrong in two opposite directions. The first wrong version says string theory was always nonsense, a 50-year scam, and now even its founders admit it. That version is false, and tonight you will see exactly why. String theory contains some of the most profound and most rigorously verified mathematics in the history of human thought, and it achieved something no other framework has ever achieved. Something we will spend a full chapter on. Susskind himself, in the same interview, in the same breath as his admissions, called it a spectacular achievement, and he is right. The second wrong version says, nothing is really wrong, that this is just a theory in progress, and the critics are exaggerating. That version is also false, because the problems we are going to walk through tonight are not loose ends. They are structural. They sit in the foundations. And the man telling you they sit in the foundations helped pour the foundations. Here is the question this video is built around, and I want to pose it plainly, because by the end of tonight you will have the full answer. The title of tonight's story says there is a crisis in string theory, and that it is worse than you think. So the question is, how bad is it, really? What exactly is broken? Is it one problem, or many? Can it be fixed? Or is physics standing somewhere it has never stood before? I will tell you now, the answer is not what the theory's critics think, and it is not what its defenders think either. The full accounting has to wait until you understand the pieces. But I promise you this, by the end of tonight, you will know exactly why the crisis is worse than you think, and also, strangely, why that might be the most hopeful thing about it. To get there, we have to do this properly. The long way around. We have to understand what string theory actually is, and why physics wanted it so desperately in the first place. We have to watch it being born, by accident, as a wrong answer to a completely different question. We have to watch it conquer physics, absorbing the careers of thousands of the smartest people alive. We have to give it full credit for what it truly accomplished, because the crisis means nothing if you think the theory was empty. And then, one by one, we have to walk into the three cracks. A symmetry that the theory cannot live without, and that our universe refuses to have. A catalogue of possible universes so enormous that the theory stopped being able to predict anything at all. And deepest of all, the problem hiding inside that phrase of Susskind's, the wrong kind of world. A mismatch between the shape of the universe the mathematics can describe and the shape of the universe you are lying in right now. And underneath all of it, holding every piece together, there is the human crack, the one about fear. Because it turns out that the crisis in string theory is not only about equations. It is about what happened to an entire field of science when one beautiful idea became the only safe thing to work on. Susskind said something else in that interview, something we will come back to near the end of the night. He said that moving into the unknown takes not only great brilliance, it takes some courage. Keep that word, courage, somewhere near the phrase, the wrong kind of world. Tonight is the story of what happens when a science runs out of one while living in the other. So let us begin where every crisis begins, not with the failure, with the dream. Because you cannot understand why this admission matters until you understand what string theory was supposed to be, and why, for a while, it looked like the answer to the oldest question physics has ever asked. Physics, at its heart, has always been a project of merging. Every great leap forward in the history of the subject has been a moment when two things that looked completely different were revealed to be one thing, seen from two angles. Isaac Newton merged the falling apple with the orbiting moon, and the result was universal gravitation. James Clerk Maxwell merged electricity with magnetism, and the result was light. Einstein merged space with time, and the result was relativity, and then he merged gravity with geometry, and the result was the general theory of relativity, the most beautiful physical theory ever written down. Each merger explained more with less. Each one took two books of rules and rewrote them as one. By the middle of the 20th century, that long project of merging had run into a wall, and the wall was physics itself. Because the 20th century produced two towering theories, and they do not get along. The first is general relativity, Einstein's theory of gravity. It describes the universe at its largest, the bending of starlight, the expansion of space, the slow spiral of galaxies, the existence of black holes. It is smooth, continuous, geometric. In general relativity, space-time is like a calm, elastic sheet, curving gracefully in the presence of matter. It has been tested from the orbit of Mercury to the collision of black holes a billion light-years away, and it has never failed. The second is quantum mechanics, the physics of the very small. It describes atoms, electrons, light, and the three forces that operate inside matter: the electromagnetic force, the strong nuclear force, and the weak nuclear force. Its mature form, quantum field theory, gave us the standard model of particle physics, which has been confirmed in some of its predictions to about 1 part in a billion. That is like measuring the distance from New York to Los Angeles and being right to within the width of a human hair. Quantum mechanics is not smooth. It is grainy, jumpy, probabilistic. Beneath its calm averages, the quantum world seethes. The vacuum itself, empty space, boils with fluctuations, particles and fields flickering in and out of existence on timescales too short to imagine. Now here is the problem, and it is worth feeling it, rather than just hearing it. Each of these theories claims to describe the same universe, and each one, pushed into the other's territory, produces nonsense. If you take quantum field theory and try to include gravity, treating gravity's carrier particle the way you treat the photon, the calculations explode. You get infinities, and not the tame kind of infinities physicists learn to cancel in other theories. Untamable ones. Every attempt to compute what quantum gravity does at short distances gives the answer, infinity, which in physics is not an answer. It is the mathematics telling you that you have asked a question with the wrong theory. And if you go the other way, if you take Einstein's smooth, elegant spacetime and zoom in far enough, quantum mechanics guarantees that the smoothness cannot survive. At a scale called the Planck length, about 10 to the minus 35 meters, 100 billion times smaller than a proton, the quantum jitter of spacetime itself should become as large as spacetime itself. The calm, elastic sheet tears into foam. Geometry stops meaning anything, and general relativity, which is a theory of geometry, stops meaning anything with it. For most everyday purposes, this divorce does not matter. Gravity is so feeble compared to the other forces, about 10 to the 36 times weaker than electromagnetism, that in any laboratory experiment you can simply ignore it, and in any planetary calculation you can ignore the quantum. The two theories rule separate empires and rarely meet, but the universe does not respect that truce. There are places where the two empires are forced into the same room, the center of a black hole, where an enormous mass is crushed toward a point, is a place where gravity is overwhelming and the distances are quantum. The first moment of the Big Bang, when the entire observable universe was compressed into a region smaller than an atom, is another. If you want to know what actually happens at the heart of a black hole, or what actually happened at the beginning of time, you need a theory that speaks both languages at once. You need quantum gravity. And for most of a century, nobody could build one. I want you to sit with how strange that is. Physics can predict the magnetic behavior of an electron to 12 decimal places. It can detect the collision of two black holes by measuring a distortion in space smaller than 1,000th the width of a proton. And yet it cannot tell you, even in principle, even roughly, what is happening at the center of the black holes it detects. The deepest places in the universe, the origin of everything, and the interior of its most extreme objects, are blank pages. Not because we have not looked, because our two best theories, each perfect in its own domain, contradict each other exactly there. That is the wound string theory was supposed to heal, and it was supposed to heal it in the most ambitious way imaginable. Not by gluing the two theories together at the seam, but by replacing both of them with something deeper, one framework from which gravity and the quantum and everything else, all the particles, all the forces, all the constants of nature, would emerge as consequences. Physicists have a name for that dream. They call it a theory of everything, one mathematical structure, maybe one equation, from which the entire book of nature could be derived. The mass of the electron, why it has the value it has. The strength of the forces, why they are what they are. The number of dimensions of space, why there is a universe with these laws instead of some other laws or no laws at all. That is what was being promised in the 1980s and 90s when string theory rose to power. That is the size of the ambition you have to hold in your mind to understand everything that follows. The claim was never merely, here is a clever idea about particles. The claim was, this may be the final theory, the last one, the framework under all frameworks. Brilliant people believed it. Entire departments reorganized around it. A generation of the most talented students on Earth chose their careers because of it. And here is the thing you should keep in your pocket for the rest of the night. That original wound, the incompatibility of quantum mechanics and gravity, was real, and it is still real. Whatever happens to string theory, that problem does not go away. Somewhere in nature, right now, at the core of every black hole in every galaxy, the two rulebooks are being reconciled somehow, because the universe does not crash. Reality runs smoothly through the very places our mathematics cannot follow. The universe knows something we do not. String theory was humanity's boldest guess at what that something is. So it matters enormously whether the guess was right. And to judge that fairly, you need to see where the guess came from. Because here is the first surprise of the night, and it is a beautiful one. String theory was not designed to be a theory of everything. It was not designed at all. It was found, lying inside a formula from the 1700s, by people who were trying to answer a completely different question, about a completely different force, at a completely different scale of nature. And the story of how a failed theory of nuclear physics accidentally became a candidate theory of all reality is one of the strangest stories in the history of science. The year is 1968, and physics is drowning in particles. For 2 decades, accelerators have been slamming protons into targets and shaking loose a zoo of new, short-lived particles called hadrons, dozens of them, then hundreds, each with its own mass, its own spin, its own decay pattern. Nobody knows what organizes them. The strong nuclear force that binds them is too strong for the standard calculational tools, which work by treating forces as small corrections. The strong force is not a small correction. It is the strongest thing in nature. The theories that tamed electromagnetism simply break when pointed at it. At CERN, the European laboratory, straddling the border between Switzerland and France, a young Italian physicist named Gabriele Veneziano is staring at the data from these hadron collisions, looking for patterns. And he notices something that should not be possible. The scattering behavior of these particles, the way the probabilities rise and fall with energy and angle, is matched, with eerie precision, by a single compact formula. Not a formula he derived from a theory, a formula he recognized. It had been written down 2 centuries earlier by the Swiss mathematician Leonhard Euler, one of the most prolific minds who ever lived. It is called the Euler beta function, and it had been sitting in the mathematics library for 200 years, an elegant little curiosity about how certain integrals behave. Veneziano found that this antique expression described the fresh data coming off the world's most advanced machines. Imagine that moment. You are looking for the law governing the newest, most confusing objects ever discovered, and you find it already written, in an old book, by a man who died before the atom was accepted as real. Veneziano published the formula in 1968. It worked, and nobody, including Veneziano, knew why. It was an answer without a question, a melody without an instrument. What physical object, what actual thing in the world, scatters in exactly the way Euler's function describes? For 2 years, that question hung in the air. And then, in 1969 and 1970, 3 physicists found the instrument. They found it independently, in 3 different places, unaware of one another, which is often how it goes when an idea's time has come. In Chicago, Yoichiro Nambu, a quiet, Japanese-born genius, who would later win a Nobel Prize for other work. In Copenhagen, a Danish physicist named Holger Beck Nielsen. And in New York, a young professor at Yeshiva University, an ex-plumber from the Bronx, named Leonard Susskind. Picture Susskind in that moment, because he has described it as one of the emotional peaks of his life. He is in his early 30s, working at the edge of exhaustion, turning Euler's formula over and over, and then he sees it. The formula is not about points. Every particle physics calculation before this moment treated particles as points, dots of nothing with properties attached. But the beta function is whispering about something else. It is the mathematics of 2 elastic objects colliding, stretching, spinning, vibrating. It is the mathematics of strings, little one-dimensional filaments, like rubber bands, like violin strings, whose different modes of vibration would appear, to any instrument too coarse to see the string itself, as different particles. Susskind was so electrified by the discovery that he later said he felt, for a moment, like he had seen something no human being had ever seen, a new layer of the world. He rushed to share the result, and one of the first senior colleagues to hear it dismissed the idea flatly. Susskind has described going home devastated, convinced for a night that his greatest insight had been strangled at birth. It had not. The strangling would come later, and from an entirely unexpected direction. Through the early 1970s, this string picture of hadrons, called the dual resonance model, was a serious, active research program. Hundreds of physicists worked on it, and then it began to die, for 3 reasons, each one apparently fatal. First, the mathematics only stayed consistent if the universe had 26 dimensions, which, you may have noticed, it does not appear to have. Second, the theory stubbornly predicted a particle that moves faster than light, called a tachyon, which in quantum theory is not really a particle at all, but a signal that your entire construction is unstable, like a pencil balanced on its tip. And third, the theory kept predicting a particle that no hadron experiment had ever seen or would ever see. A particle with no mass at all, spinning with exactly 2 units of spin. No massless spin 2 hadron exists. The prediction would not go away. It was baked into the structure. Every version of the theory contained this ghost. Meanwhile, next door, a rival theory of the strong force was coming together fast. It was called quantum chromodynamics, the theory of quarks and gluons, and by 1973 it had done what the string model could not. It explained the hadron zoo cleanly. It fit the data from a new generation of experiments, and it slotted perfectly into the quantum field theory framework that already ruled the other forces. The competition was over. Quantum chromodynamics won the strong force, completely and permanently. The string model was abandoned almost overnight. The conferences dried up, the funding moved on, and the physicists moved with it. By 1974, string theory was a dead theory of the wrong thing. And this is where the story takes the turn that changes everything. Because two physicists, Joël Chirc in France and John Schwartz at Caltech, were still staring at the corpse, and specifically at the ghost, that massless spin-2 particle, the embarrassing prediction that would not leave, and they asked the question that sounds obvious only in hindsight. What if the theory was never wrong about the particle? What if it was wrong about the subject? Because there is exactly one place in physics where a massless spin-2 particle is not an embarrassment, but a requirement. Any quantum theory of gravity must contain one. It even has a name waiting for it, the graviton, the quantum carrier of the gravitational force, the particle of gravity itself, never observed, but demanded by the logic of quantum field theory. In 1974, Chirc and Schwartz published their proposal. String theory is not a theory of hadrons. It is a theory of quantum gravity. The strings are not the size of protons. They are 10 to the minus 35 meters long, the Planck length, 19 orders of magnitude smaller than anyone had been imagining, vibrating at the very floor of reality. And that ghost particle, the one that killed the theory as nuclear physics, is the graviton. Gravity had not been put into string theory. Nobody put it in. It had been sitting inside the mathematics from the very first day, unwanted, unremovable, waiting for someone to recognize its face. Stop and feel how upside down that is. Physicists had spent 50 years failing to force gravity into quantum theory. Every attempt by hand had collapsed into infinities, and here was a theory, built by accident for a completely different purpose, that would not stop doing quantum gravity even when everyone begged it to stop. To this day, that remains string theory's strangest credential, and its most seductive one. It is a theory that predicts gravity. As Susskind and others have often put it, if we did not already know gravity existed, string theory would have told us to go looking for it. You might expect that the physics world dropped everything on the spot. It did not. Almost nobody switched fields. The standard model was conquering everything in sight. There was a decade of glorious experimental confirmations ahead, and quantum gravity was considered a philosophical luxury, unmeasurable, and therefore unserious. For 10 years, string theory, as a theory of gravity, was kept alive by a handful of people, most famously Schwartz, working in near isolation at Caltech, in what he later described as a very lonely decade. The theory that would soon swallow physics whole was, through the late 70s and early 80s, one of the least fashionable subjects a young researcher could touch. Remember that detail. Hold it next to the fear that Susskind describes among today's young physicists. Because the great irony of tonight's story is that string theory itself was born from exactly the kind of unfashionable, career-risking stubbornness that its own dominance would later train out of the field. Then, in the autumn of 1984, everything changed in a single month, and the quiet decade ended with a stampede. By 1984, string theory as a theory of gravity had one gigantic problem hanging over it, a technical time bomb called an anomaly. An anomaly, in this context, is a defect where a symmetry that the mathematics depends on is quietly broken by quantum effects, and when that happens, the theory begins predicting nonsense, probabilities that do not add up to one, particles created from nothing. It was widely expected that string theory, examined closely enough, would turn out to be anomalous, and that would be that. A clever idea, fatally ill. In August of 1984, Michael Green and John Schwartz sat down to compute the anomaly directly, expecting, like everyone else, to find a non-zero answer. What they found instead was a miracle of cancellation. Term after term, page after page, the potentially fatal contributions arrived in perfectly matched pairs with opposite signs, and the total came out to exactly 0, but only for very specific mathematical structures, only for particular symmetry groups. The theory was not sick. It was consistent, and consistent in a razor-thin, non-negotiable way, as if the mathematics had been waiting to demonstrate how carefully it was built. The reaction was unlike anything in the modern history of theoretical physics. Within weeks, the most influential theorists in the world dropped what they were doing. Within months, hundreds of physicists had switched fields. Within a couple of years, string theory went from a fringe pursuit kept alive by a handful of believers to the dominant research program in fundamental physics, and it would hold that dominance for the next 3 decades. People who lived through it called it the first superstring revolution, and the word revolution is not an exaggeration. It rearranged departments, careers, and the entire aspiration of the field, because the theory that had just proven itself consistent did not merely include gravity. It seemed, for one intoxicating stretch of years, to include everything. Here is the picture that emerged through the late 1980s. The consistent versions of the theory, and there turned out to be exactly 5 of them, with names like Type 1, Type 2a, Type 2b, and 2 so-called heterotic theories. All required 2 things. They required supersymmetry, an additional symmetry of nature that we will meet properly and fatefully later tonight. That is the super in superstring, and they required the universe to have not 4 dimensions of space-time, but 10, 9 of space and 1 of time. 10 dimensions sounds like a deal-breaker. It is not, and the reason it is not was worked out in 1985 in a landmark paper by Philip Candelas, Gary Horowitz, Andrew Strominger, and Edward Witten. The 6 extra dimensions they showed could be curled up, compactified is the technical word, into a tiny knotted shape at every point of our familiar space, a shape far too small to see, potentially as small as the Planck length itself. Think of a garden hose seen from an airplane. From high above, it is a one-dimensional line. Walk up to it, and you discover that at every point of that line, there is a small extra circle, a dimension you could not see from far away. Now replace that simple circle with a 6-dimensional knot of extraordinary intricacy, a shape called a Calabi-Yau space, named for the mathematicians Eugenio Calabi and Xing-Tong Yau, and attach one to every point of space. That is the string theorist's universe. And here was the beautiful part. The part that made sober people talk about the end of physics. The geometry of that hidden shape determines the physics we see. The number of holes in the knot determines how many families of particles exist. The way strings wrap and vibrate around it determines the forces, the masses, the charges, everything arbitrary about our universe, all the unexplained numbers in the standard model, would be explained by the shape of a hidden 6-dimensional space. Physics would become geometry, just as it had for Einstein, but now all the way down. For a while, it truly seemed close. There was talk in the late 80s that the final theory might be finished within a decade. Then progress slowed, questions accumulated, and the 5 theories sat there, 5 of them, which was 5 times too many for a theory of everything. If string theory was the unique answer, why did it come in 5 flavors? The second revolution answered that, and it arrived in 1995, delivered largely by one man. Edward Witten is a figure without parallel in modern physics, a theorist of such power that in 1990 he had become the first physicist ever to win the Fields Medal, the highest honor in mathematics. File that fact away. It is going to matter later, in a way that stings. At a conference in March 1995, Witten laid out evidence that the 5 string theories were not 5 theories at all. They were 5 limits of a single, deeper, 11-dimensional structure, 5 views through 5 windows into one building. The 5 theories were connected by transformations called dualities, exact equivalences showing that what looks like a strongly interacting regime of one theory is secretly a weakly interacting regime of another, that big, curled-up dimensions in one description are small ones in another. The hidden master framework was named M theory, and Witten was famously coy about what the M stood for. Magic, mystery, or membrane, he suggested, according to taste. The second revolution brought new objects into the theory, and one class of them would quietly become the most important tool in everything that follows. Joseph Polchinski proved that string theory contains not only strings, but membranes of various dimensions, surfaces called D-branes, on which the endpoints of open strings are anchored. A D-brane is like a wall in the higher dimensional space, and strings attached to it behave like particles trapped on that wall. D-branes turned out to be the key that unlocked string theory's greatest verified triumph, which is the subject of the next chapter, and they spawned entire pictures of reality in which our whole visible universe is itself a 3-dimensional brane floating in a higher dimensional space. But step back from the mathematics for a moment, because the sociology of these years is a load-bearing part of tonight's story. From 1984 onward, string theory did not merely lead theoretical physics, it absorbed it. It became, at the top American and European institutions, close to the only game in town for a young theorist with ambitions in fundamental physics. The best graduate students were funneled toward it, because that was where the advisors were, and the postdoctoral jobs, and the prestige. Faculty positions in fundamental theory went overwhelmingly to string theorists. Alternative approaches to quantum gravity survived at the margins, in a few determined groups, but a young physicist who chose them was making a career gamble, and everyone knew it. None of this was a conspiracy. No committee met in a smoky room and decreed it. It was the ordinary, human dynamics of a field betting on its best horse, compounding year after year, until the bet had become the stable, and the stable had become the whole farm. And through all these years of conquest, of revolutions and medals and magazine covers, there was one thing string theory had not done. It had not made contact with a single experiment, not one measured number predicted in advance, not one confirmation. The theory's characteristic scale, the Planck length, sits so far below anything a particle accelerator can probe that direct tests were out of the question from the start, and the indirect hopes, the signatures that might have shown up, had not shown up. In the glow of the revolutions, that silence was easy to explain away. The mathematics was so rich, so interlocking, so miraculously consistent that it felt true. Witten himself expressed the mood of an era when he said that string theory was a piece of 21st century physics that had fallen by accident into the 20th century. The experiments would come. The universe would cooperate. It was only a matter of time. The universe, as we are about to see over the rest of tonight, had other plans. But before we watch the cracks open, honesty demands that we spend one full chapter on what the conquest actually brought. Because the great irony of the crisis is this. In the exact years when string theory was failing to describe our universe, it was succeeding at something else, something arguably more profound. It was quietly solving the deepest paradox in gravitational physics, and proving, once and for all, that quantum mechanics and gravity can live together, just as it would turn out, not here. If you want to understand why the crisis in string theory is a tragedy and not a scandal, you have to understand this chapter, because the theory's defenders are not deluded. String theory earned its reputation. It earned it with 3 achievements, each one real, each one profound, and the third one so strange that it changed what physicists believe reality is made of. Susskind, in the same interview, where he declared the theory certainly not a description of our world, insisted with equal force on this half of the ledger. String theory, he said, is not a failure. It is a spectacular achievement. Both sentences are true at once, and holding them together is the whole art of tonight. The first achievement is the existence proof. Remember the wound from earlier, the century-long incompatibility of quantum mechanics and gravity, the infinities, the mutual contradiction at the foundations of physics. Before string theory, it was a live possibility that quantum mechanics and gravity simply cannot coexist, that the universe is built on two rulebooks that no consistent mathematics can ever contain at once. That possibility is now dead. String theory killed it. Within string theory's mathematics, at least in certain settings, gravity and quantum mechanics function together, exactly, without infinities, without contradiction, to every order anyone has checked. Susskind's words, "It is an existence proof that quantum mechanics and gravity can coexist with each other." For many years, he said, people thought they were at each other's throats. We now know, with certainty, that they are not, because here is a mathematical world, fully consistent, that contains both. That is no small thing, he said. That is a big thing. Even if string theory turns out not to describe our universe, this result stands forever. Reconciliation is possible. Somebody in the space of all mathematics has done it. The question that remains, and it will haunt the rest of tonight, is whether it can be done in a universe shaped like ours. The second achievement concerns black holes, and it is the closest thing string theory has to a verified prediction. In the early 1970s, Jacob Bekenstein and Stephen Hawking discovered something that should have been impossible. Black holes have a temperature, and they have entropy. Entropy, loosely, is a count of hidden microscopic arrangements, the number of ways you could rearrange a system's smallest parts without changing how it looks from outside. A box of gas has entropy because the molecules could be arranged countless different ways. But a black hole, according to general relativity, has no parts. It is bald, featureless, defined completely by its mass, its spin, and its charge. And yet Hawking's calculation assigned it an entropy, an enormous one, proportional, bizarrely, not to the hole's volume, but to the surface area of its horizon. The formula is carved on Hawking's memorial stone in Westminster Abbey. It contains a mysterious factor of 1/4, 1/4 of the horizon area measured in Planck units. For 20 years, that formula was a riddle. If entropy counts arrangements, what exactly is being arranged? What are the microscopic parts of a black hole? In 1996, Andrew Strominger and Kumran Vafa answered it. Using string theory's D-brains, they built a certain kind of black hole out of its microscopic string-theoretic constituents, the way you might build a gas out of molecules, and then they simply counted the quantum arrangements of those constituents. The count came out to exactly the Bekenstein-Hawking formula, the area, the Planck units, the factor of 1/4, not approximately, not up to a fudge factor, exactly. A theory invented for hadrons, resurrected for gravity, had reached into the most mysterious formula in physics and derived it from first principles. When physicists say string theory is a real theory of quantum gravity and not just a hope, this calculation is Exhibit 1. Nature had left one number lying at the intersection of gravity, quantum mechanics, and thermodynamics, and string theory walked up and explained it. The third achievement is the strangest, and it is Susskind's own. It begins with a question that sounds childish. Where is the stuff in a room? Try this as you lie there. Take stock of the space around you right now. The bed beneath you, the air above you, the walls holding the dark in place, your own body, resting. The ordinary description of all of this, the one physics has used for a century, says that fields fill the space of the room, quantum fields, and their local vibrations are the particles making up everything in it, and every object, every atom of you, is located somewhere in the room's three-dimensional interior. Stuff lives in space. Nothing could be more obvious. Now hold that picture while I tell you what quantum gravity found. Through the 1990s, following clues from black hole physics, Gerard Hooft, and Leonard Susskind proposed something called the holographic principle. Here is Susskind's own version of it, the version he gave in the interview, sitting in a room just like yours. "The room is filled with stuff," he said. "The ordinary description is quantum fields and particles in the room. But in quantum gravity, we now know that the correct, precise description of everything in the room is a theory that lives on the walls of the room. Not in the room, on its boundary. Every degree of freedom, every bit of information needed to describe the interior completely, you, the bed, the air, every atom, can be accounted for by a theory defined purely on the enclosing surface, with no interior at all. The clue came from those black holes. A black hole's information content scales with its surface area, not its volume, and a black hole is the densest information storage the universe allows. Which means the information in any region of space is bounded by its area. Which means, if you follow the logic all the way, the three-dimensional interior is not fundamental. It is more like a projection, a rendering, of data that lives on a distant two-dimensional surface. The word hologram is not a metaphor chosen for drama. On an ordinary hologram, a flat piece of film encodes a full three-dimensional image. The proposal is that reality has that structure. Depth itself, the third dimension, the inness of things, may be emergent. When 't Hooft and Susskind proposed this, it sounded like philosophy. In 1997, a young Argentine physicist named Juan Maldacena made it mathematics. He discovered a concrete, exact equivalence between two theories that could not look more different. On one side, string theory, with gravity, strings, black holes, the works, living inside a certain kind of curved space-time. On the other side, an utterly ordinary quantum field theory, with no gravity and no strings at all, living on that space-time's boundary, one dimension down. Everything that happens in the gravitational interior, the bulk, corresponds exactly to something happening in the boundary theory. A black hole forming and evaporating in the bulk is, in the boundary description, nothing but hot particles thermalizing and cooling, a process as ordinary as coffee going cold, and one that manifestly does not destroy information. This correspondence became the most cited result in the history of high-energy physics, on the order of 20,000 citations, a number essentially without precedent. It is the sharpest form of the holographic principle. It is why the consensus of the field concluded that Hawking was wrong and black holes do not destroy information, and it has escaped its home territory entirely. Physicists have used it as a calculating device for the quark-gluon plasma created in heavy ion colliders, and for exotic superconductors, real laboratory systems, because sometimes the easiest way to compute the behavior of a strongly interacting quantum system is to translate the problem into a fictitious gravitational world, one dimension up, solve it there, and translate back. Let all of that settle for a moment, because this is the high watermark of the story, and it deserves to be felt without irony. A theory found by accident in an 18th century formula had, by the turn of the millennium, proven that quantum mechanics and gravity can coexist, derived the entropy of black holes exactly, resolved the deepest paradox Hawking ever posed, and revealed that space itself may be a hologram, that the world may be written on its edges rather than filled through its middle. Whatever else is true, the people who built this were not chasing nothing. They touched something profound in the structure of mathematics and, quite possibly, of reality. But you may have noticed a phrase sliding past, quietly, several times in this chapter. In certain settings, in a certain kind of curved space-time. Every one of these triumphs, the existence proof, the entropy count, Maldacena's correspondence, all of them live in the same very particular mathematical territory, a space-time with a special shape, a special sign of curvature, a space-time with a boundary, a wall at infinity for the hologram to live on. There was always a question, patient and quiet, waiting at the edge of the celebration. Is our universe that kind of space-time? 28 years ago, while the field was celebrating Maldasena's discovery, astronomers pointing telescopes at exploding stars were, at that very moment, collecting the data that would answer the question. The answer was no. We come now to the first crack, and to see it clearly, you need to understand the single most important word in string theory's name. Not string, super. Supersymmetry is a proposed symmetry of nature, and a symmetry, in physics, is a statement that the world looks the same after some change. Rotate a perfect sphere, and nothing changes. Shift an experiment from Monday to Wednesday, and the laws behave identically. The great insight of 20th century physics, owed largely to the mathematician Emmy Noether, is that symmetries are not decorations. They are the underlying structure. Every symmetry of nature enforces a conservation law, and the symmetries of the known laws dictate nearly everything about them. So when physicists in the 1970s discovered, on paper, a completely new kind of symmetry, one that no one had thought possible, it was an event. All the particles of nature fall into two great families: fermions, the particles of matter; electrons, quarks, neutrinos, the loners of the universe, no two of which can occupy the same state, which is why matter is solid and atoms take up space; and bosons, the particles of force; photons, gluons, the joiners, which happily pile into the same state, which is why laser light exists. These two families have utterly different personalities, and they were thought to be forever separate. Supersymmetry is the proposal that they are secretly the same family, that there exists a transformation turning fermions into bosons and bosons into fermions, and that the laws of nature do not notice the swap. If supersymmetry were an exact symmetry of our world, every particle would have a partner, a shadow twin from the other family. The electron, a fermion, would have a boson partner, dutifully named the selectron. Every quark would have a squark, the photon would have a photino, the graviton a gravitino, an entire mirrored population of matter weaving through the world. Now, why would anyone believe in such a thing without evidence? 3 reasons, and they were good ones. First, supersymmetry tamed a famous sickness in the Standard Model, called the hierarchy problem, the mystery of why the Higgs boson's mass, and with it the scale of all masses, is so absurdly, precariously small compared to the Planck scale. Quantum corrections should drag the Higgs mass upward by 17 orders of magnitude, and in the Standard Model, they are prevented from doing so only by a cancellation so miraculous it looks like the universe is cheating. With supersymmetry, the cancellation is automatic. Every dangerous correction from a particle is cancelled by an equal and opposite correction from its superpartner, pair by pair, like a ledger that balances itself. Second, if you took the 3 non-gravitational forces and traced their strengths toward higher and higher energies, in a supersymmetric world, the 3 lines met at a single point, hinting at one unified force at the root of everything. Third, the lightest superpartner would have been stable, invisible, and abundant, a perfect candidate for the dark matter that outweighs ordinary matter 5 to 1 in our universe. One idea solved 3 of the deepest problems in physics simultaneously. That is why thousands of physicists spent their careers on it. It was not fashion. It was the best motivated speculation of its era. And for string theory, supersymmetry was not even a speculation. It was oxygen. Here is the part that matters most tonight, so let me be precise. The consistent string theories, all 5 of them, are supersymmetric string theories. Supersymmetry is what exorcises the tachyon, that faster-than-light instability that killed the original bosonic string. Supersymmetry is what allows the anomalies to cancel, the 1984 miracle. Supersymmetry is what makes the mathematics solvable at all, what makes the black hole entropy countable, what holds Maldasena's correspondence rigid. Remove it, and the calculations that made string theory's reputation do not merely get harder, they stop existing. Susskind, in the interview, put it without any cushioning. String theory, he said, fails when you don't make it supersymmetric. So the question of whether our universe is supersymmetric became, quietly, a question about whether our universe is the kind of world string theory describes. And that question, unlike almost everything else in this story, could actually be tested. Supersymmetry, if it exists at all, must be a broken symmetry, hidden at low energies, because a selectron with the electron's mass would have been discovered in the 1950s. The superpartners, if real, must be heavy. But the same arguments that motivated supersymmetry, especially the hierarchy problem, said they should not be too heavy. They should be within reach of a sufficiently powerful collider, clustered around the energy scale of the Higgs itself. This was the great promise repeated through the 1990s and 2000s. The Large Hadron Collider, the 27-kilometer ring under the French-Swiss border, the most complex machine human beings have ever built, would find them. Simulations were run. Discovery papers were drafted in advance. A generation was hired on the expectation. The Large Hadron Collider switched on in earnest in 2010. In 2012, it found the Higgs boson, a monumental confirmation of the Standard Model, at a mass of about 125 giga-electron volts. And then it went hunting for the superpartners. It has now run for a decade and a half, at collision energies up to 13.6 trillion electron volts, recording quadrillions of collisions, with 2 independent multi-thousand-person experiments sifting the debris. The result is one of the loudest silences in the history of science. Nothing. No selectrons, no squarks, no gluinos, no photinos. Search after search has come back empty, pushing the possible masses of the simplest superpartners above roughly 2 trillion electron volts, far beyond the range where they would naturally solve the problems they were invented to solve. The beautiful cancellations, the meeting of the force lines, the dark matter candidate, all of it now requires the superpartners to be hiding in ever more contrived corners, and with every empty search, the contrivance grows. Susskind, in the interview, described the psychology of those decades with the bluntness of a man too old to flatter anyone. For years, he said, people made these theories in which an approximate supersymmetry would be discovered at the very, very next accelerator experiment, with no good reason. No good reason, he repeated. It's just they wanted it to be true. And here we arrive at the sentence on which the whole crisis turns. Not a hostile physicist's sentence. Susskind's own. We know for certain, he said, that the world we live in does not have those special features. Exact supersymmetry, and the other special mathematical properties that make capital S string theory precise and solvable. Among them, note this for later, a cosmological constant of exactly 0, are features our universe measurably, demonstrably lacks. The one string theory that exists as precise mathematics is a theory of a world that is not this one. The natural response, the one physicists reached for immediately, is, fine, then break the symmetry. Build the version of string theory where supersymmetry is imperfect, hidden, spontaneously broken, the way other symmetries in nature are known to break. Surely the exact theory is just the idealized case, and the real world is the slightly messy version. Here is Susskind's answer, and I want you to hear how complete it is. People talk about it all the time, he said. They talk about breaking supersymmetry, blah blah blah. But there is no real theory of that. There is no known, non-supersymmetric string theory. Not a difficult one. Not an ugly one. None. The older generation attacked the problem for years, and every attempt fell apart in instabilities and inconsistencies. And then he added the confession that gives the statement its weight. I worked on it, he said, and I failed. That's not a criticism of anybody. It's a fact. Let the shape of this settle over you, slowly, because it is the emotional center of the first crack. Everything that makes string theory exact, everything that makes it trustworthy, its consistency, its solvability, its miraculous cancellations, flows from supersymmetry, and supersymmetry is precisely what our universe declines to have. The theory's rigor and the theory's wrongness are not two facts, they are one fact. The very features that let physicists prove things about string theory are the features that separate it from reality. Thousands of brilliant careers spent perfecting the mathematics of a world that is not ours. Not wasted, as we have seen, the achievements are real, but aimed, all along, at a universe next door. Susskind's verdict on the situation has the tone of a man staring at an unpaid debt. That is intolerable, in a sense, he said. It can't stay that way. We have to describe our world. That's our purpose. Hold on to that word, intolerable, because you might think a missing symmetry is as bad as it gets, that this is the crack the title of tonight's story was warning you about. It is not. We are only at the first of three. The second crack is stranger. It comes not from something string theory lacks, but from something it has far, far too much of. Because when physicists tried to count how many different universes string theory could describe, the answer that came back was not 1, and it was not 5. It was a number so large that it broke the theory's ability to say anything at all. There was a promise buried in string theory's design, and in the beginning, it was counted among the theory's greatest virtues. The theory has no adjustable constants. The standard model of particle physics, for all its precision, is riddled with numbers that have to be measured and inserted by hand, about 20 of them, the masses of the particles, the strengths of the forces, numbers physics can use but cannot explain. String theory was supposed to end that. In string theory, there is nothing to adjust. Every number that describes a universe, every mass, every coupling, every constant, is supposed to emerge as an output of the equations. Susskind described this in the interview with characteristic plainness. The behavior of space-time and the constants of nature, he said, are not an input. It's an output of some equations. Then comes his next sentence, and inside it, the second crack. And those equations, he said, have many, many solutions. Here is what that means, and why it matters more than it sounds. A solution of string theory's equations is not a small thing, like a solution of a homework problem. Each solution is a complete possible world. Physicists call each one a vacuum, a stable configuration of the theory, and each vacuum comes with its own fully furnished physics, its own roster of particles, its own forces with their own strengths, its own masses, its own constants, its own cosmological behavior. Choose a different solution, and you have not adjusted a universe. You have replaced it. In one solution, there are electrons 2,000 times lighter than the proton, as in ours. In another, Susskind noted, electrons 2,000 times heavier. In some, the force we call electromagnetism does not exist. Each solution is, in every meaningful sense, a different possible universe. So the decisive question became, how many solutions are there? If the answer were 1, string theory would be the final theory in the strongest imaginable sense. The universe derived uniquely from pure consistency, every constant of nature explained forever. Through the 80s and 90s, that was the hope burning under the whole program. If the answer were a handful, physics could test its way through them like keys on a ring. The answer began arriving around the turn of the millennium, as theorists learned to count the ways the 6 hidden dimensions can be configured. Recall the Calabi-Yau spaces, those knotted 6-dimensional shapes curled up at every point of our space, whose geometry determines all visible physics. It turns out the knot is not the only choice to make. Through the shape's hundreds of holes and handles, string theory allows generalized magnetic fluxes to be threaded, like invisible field lines wrapped through each opening, and each threading changes the resulting universe. Each hole admits many possible flux values, and a typical Calabi-Yau has hundreds of holes. The combinations multiply. By 2003, in constructions developed by Shamit Kachru, Renata Kalosh, Andre Linde, and Sandip Trivedi, and in the counting arguments that followed, The estimate stabilized at a number that has become the most famous and most infamous number in modern theoretical physics, 10 to the 500, a 1 followed by 500 zeros, that many distinct solutions, that many possible universes, each fully consistent, each wearing different laws. I promised earlier that I would always try to give you numbers you can feel, so let me try, and let me confess in advance that this one defeats all comparison. The number of atoms in the entire observable universe, every atom in every star, in every one of 2 trillion galaxies, is about 10 to the 80. If every single atom in the universe contained, inside itself, another entire universe of atoms, and you counted every atom in all of those universes within universes, you would have 10 to the 160. You would need to nest entire universes inside atoms 6 times over before your count of atoms approached the count of string theory's solutions. 10 to the 500 is not a large number. It is a number from outside the universe's own vocabulary. And when the interviewer quoted it to Susskind, the man who coined the name for this space of possibilities, his correction was not in the direction you would hope. People always quote 10 to the 500, he said. It's much more than that. Susskind named this space of solutions the landscape. Picture it as he does, an endless terrain of valleys, each valley a stable vacuum, a possible universe, separated by mountains of instability, stretching in more directions than a mind can hold. Somewhere in that terrain, presumably, is one valley with our exact particle masses, our exact forces, our absurdly tiny cosmological constant. One valley among 10 to the 500, or, per the man himself, far more. And finding it, Susskind said, is very much looking for a needle in a haystack. Then, later in the interview, he completed the thought with the sentence that turns an inconvenience into a crisis. Even if we ignore the question of supersymmetry, he said, even setting the first crack entirely aside, it's just too many to sort through. What we do about it, I don't know. Stop and notice what has happened to the original promise. The theory with no adjustable constants, the theory that was supposed to explain every number in nature uniquely, turned out to contain every possible set of numbers somewhere in its solution space. And a theory that contains everything explains nothing. This is not rhetoric. It is close to logic. A theory earns its keep by forbidding things, by saying, this you will never see. If, for essentially any imaginable universe, string theory has a valley that matches it, then no observation can ever surprise the theory, no measurement can ever contradict it, and the theory's grip on reality goes slack. The critics of string theory regard the landscape as the moment the program stopped being predictive science in the traditional sense, and plenty of string theorists, in their honest hours, do not entirely disagree. But the landscape opened onto something even stranger, and here tonight's story links hands with a question humans have asked forever. Because a catalogue of 10 to the 500 possible universes forces the question, are the other valleys real? Is there a universe for every solution? And modern cosmology, uninvited, offers a mechanism that would say yes. The theory of eternal inflation, developed to explain the smoothness and structure of our own cosmos, describes a universe that never stops giving birth, in which quantum fluctuations forever nucleate new expanding regions, new bubbles, and each bubble can settle into a different valley of the landscape, a different vacuum, different laws. Susskind, in the interview, walked through it with care. First the caveat, the point the interviewer pressed him on. Just because equations allow something does not mean existence realizes it, he agreed, if the universe is small. But, he said, the equations of eternal inflation allow the universe to be exponentially bigger than what we see, maybe exponentially bigger. And if it is big enough, then just on ordinary probability grounds, everything possible happens somewhere. His image is the one to keep. If you wait long enough and the universe gets sufficiently big, he said, it will be filled like a patchwork quilt with regions of different properties. different constants, different particles, different skies. We would be one patch on a quilt whose size has no name, sewn from 10 to the 500 kinds of cloth. And this, finally, is where the cosmological constant re-enters our story and sets up everything that follows. In 1987, before the landscape was even a word, the physicist Steven Weinberg made an argument that half the field has never forgiven. The cosmological constant, the energy of empty space, the thing that would later be called dark energy, was then believed to be exactly zero, though nobody could explain why. Weinberg reasoned as follows. Suppose there are many regions with many different values of the constant. In regions where it is large and positive, space expands so violently that no galaxy can ever form, so no one is there to measure anything. In regions where it is large and negative, the universe recollapses into a crunch before life can arise. Only in the rare patches where the constant is almost, but not exactly, zero can galaxies, stars, and observers exist. Therefore, said Weinberg, if the many regions picture is right, we should expect to measure a cosmological constant that is not zero, merely small, just small enough to permit our existence, and no smaller. It was a prediction from what is called anthropic reasoning, the logic of we see what we see because where it is otherwise, there is no one to see. Most physicists found this style of argument repellent, an abdication of the duty to explain. And then, 11 years later, astronomers went out and measured the cosmological constant. It was not zero. It was tiny and positive, close to the range Weinberg's reasoning favored. The most hated argument in physics had made the most successful prediction about the deepest number in cosmology. For Susskind, the landscape plus eternal inflation plus Weinberg's logic assemble into a coherent, if unsettling, picture. The constants of our universe are not derived, they are environmental. They are our patch's local weather. Asked why the cosmological constant is what it is, the picture answers, because in almost every other patch, you could not exist to ask. Whether that is a profound truth, or the sound of physics giving up, is one of the great live arguments of our age. And tonight is not the night we settle it. Tonight, what matters is what the discovery of that tiny, positive number did to string theory itself. Because everything you have heard so far, the missing symmetry, the 10 to the 500 valleys, all of it, the field believed it could survive. Hard problems, yes. Deferrable problems. But that little number, the one Weinberg circled, the one the astronomers measured in 1998, turned out to have a sign, positive. And the sign of one number, it slowly emerged, points at the deepest crack of all, the one Susskind's whole warning revolves around. It determines the shape of the universe's future, the kind of world we live in. And it is, precisely, the wrong kind. Let us step back for a moment and stack the pieces, because we have crossed the midpoint of the night, and the architecture of the crisis is now half built. Physics needs a theory of quantum gravity, because at the center of black holes and at the first instant of the universe, its two great rulebooks contradict each other. String theory, born by accident, became the leading candidate, and it earned that standing with real achievements, an existence proof that gravity and quantum mechanics can coexist, an exact accounting of black hole entropy, and the holographic revelation that a world's interior can be written on its boundary. Then came the cracks. The first, the theory's precision depends on supersymmetry, a symmetry our universe has been searched for and does not show. The second, the theory's equations describe not one universe, but at least 10 to the 500, a catalogue so enormous the theory forbids nothing, and therefore predicts nothing. Two structural cracks. And yet, if those were all, string theory could still say of itself, somewhere in my landscape is your world, and someday we will find the valley. Tonight's third crack is different in kind. It is the reason Susskind does not say the theory is incomplete. It is the reason, he says, we live in the wrong kind of world. Because the mathematics of string theory, in every precise form anyone has constructed, requires the universe to have a shape, a global structure, that ours measurably does not have. To feel this crack, you only need two pictures, two kinds of universe. Hold them side by side, because the entire crisis lives in the difference between them. The first picture is called anti-de Sitter space, named for the Dutch astronomer Willem de Sitter, a contemporary of Einstein. It is a universe whose empty space has negative energy, a negative cosmological constant, and that sign gives space a gentle inward pull, a curvature that folds it up like a bowl. Anti-de Sitter space does not expand, it sits, and it has the single most important property in this whole chapter. It has a boundary. Travel outward in anti-de Sitter space, and, in a precise mathematical sense, there is a wall at infinity, an edge, a place where the universe ends, and light can travel there and bounce back to you in finite time, like a shout returning from a canyon wall. Physicists call it a time-like boundary, and you should think of it as exactly the walls of Susskind's room, scaled up to the whole cosmos. And that is what makes anti-de Sitter space the perfect home for holography. The holographic principle says the interior is described by a theory on the walls. Anti-de Sitter space comes with walls built in. Maldaceno's correspondence, the most cited result in the field, is anchored there. The boundary is where the dual theory lives, the flat screen from which the interior world is projected. Every exact statement string theory can make about quantum gravity, every proof, every entropy count, every resolution of every paradox, lives in a universe with that wall. Now the second picture. Take the cosmological constant and flip its sign. Positive. Now empty space does not pull inward. It pushes outward. Every cubic meter of vacuum carries a whisper of repulsive energy, and the more space there is, the more total push, so expansion feeds expansion. This universe does not sit, it runs. It expands exponentially, doubling and doubling without end, space itself stretching faster and faster forever. This is de Sitter space, and de Sitter space has no boundary. Travel outward as far as you like and you will never find a wall, never an edge, never a place where the cosmos ends and a boundary theory could live. What you find instead, and the difference is everything, is a horizon. Here is the scene, and I want you to place yourself inside it, because this is not a thought experiment. This is a description of where you live. Imagine you are the astronomer Susskind describes, and you can see with perfect instruments, out to any distance light permits. From your bed, look outward, past the walls of your room, past the roof of the sky, past the moon, out through the thinning stars at the galaxy's edge, out into the dark ocean between galaxies, 2 million light-years to Andromeda, then past it, 50 million, a billion, 10 billion light-years. Galaxies streaming past your view, like lights on a highway at night. And notice, as you go, that the deeper you look, the faster everything is receding, space itself swelling between you and everything else, until, at a distance of roughly 16 billion light-years, you reach a place where the arithmetic turns absolute. Out there, the space between you and those galaxies is growing faster than light itself can cross it. Light launched toward you from beyond that line swims forever against a current that outruns it. Nothing from beyond will ever reach you. Not light, not signals, not causes. It is not a wall. There is no wall there. Galaxies drift across that line and notice nothing, feel nothing, a quiet border that exists only in relation to you. It is a horizon, like a black hole's horizon, turned inside out, wrapping not around some distant object, but around you, with you at the center. Everywhere you go, every observer in a de Sitter universe is wrapped in their own private sphere of the knowable, and the sphere is shrinking, in the sense that galaxy after galaxy is slipping across it, out of reach, forever. That is your universe. That is the kind of world you live in. And in 1998, two teams of astronomers measuring the brightness of distant exploding stars discovered which picture is ours. The expansion of the universe is not slowing down, as everyone expected. It is speeding up. Empty space pushes. The cosmological constant is positive, minuscule, about 10 to the minus 122 in the natural units of gravity, but positive, and that discovery earned the Nobel Prize in 2011. Our universe is not anti-de Sitter. It is not even neutral. It is trending, with every passing eon, toward pure de Sitter space, the boundaryless, horizoned, exponentially running kind of world. Susskind, in the interview, said it with the flat clarity that makes it land. You might get the feeling that de Sitter space and anti-de Sitter space are almost the exact opposite of each other, the interviewer suggested. Yeah, more or less, said Susskind. That's correct. We live in the wrong kind of world. Now watch what this does to everything you learned tonight. The holographic principle says the interior is written on the walls. Our universe has no walls. The precise theories, the ones with proofs, live on the boundary, at spatial infinity. Our universe has no boundary at spatial infinity, only that observer-wrapped horizon. And, as Susskind explained, a horizon is not the kind of boundary the holographic principle envisions. It is not a place. It is different for every observer. It has a temperature, a faint quantum glow, discovered by Gary Gibbons and Stephen Hawking in 1977. It carries an entropy, as if the unknowable region behind it were hiding a finite number of secrets. A horizon is a strange, thermal, personal thing, and nobody knows how to hang a hologram on it. The interviewer asked the direct question. Could there be a de Sitter version of Maldasena's correspondence? A DSCFT? Suskind's answer had no hedge in it at all. No, he said. In no case. A conformal field theory is exactly the right thing for anti-de Sitter space, and exactly the wrong thing for de Sitter space, and we don't know what the right thing is. And then he said the sentence that, more than any other, justifies the title of tonight's story. No known version of string theory, no precise known version of it, exists in de Sitter space, and we live in de Sitter space. Sit with the full size of that. This is not, string theory has not yet explained our particles. This is the exact mathematical structure that constitutes string theory's claim to describe quantum gravity has no formulation in a universe with our sign of the cosmological constant. The triumphs of Part 5, the existence proof, the entropy count, the hologram, all of them were proven in the bowl-shaped world with the wall, and none of them, not one, has been carried across into the running, boundaryless world you actually inhabit. The wrong kind of world is not a poetic phrase. It is a technical diagnosis. The universe we live in is outside the theory's precise domain, and it has been, quietly, all along, through every revolution, every medal, every conquest. It gets 1 degree sharper still. Within string theory itself, a faction has argued that the mismatch is not a gap but a law. Since 2005, a research program led by Qumran Vafa at Harvard has been mapping what it calls the swampland, the set of seemingly sensible theories that cannot, in fact, be completed into consistent quantum gravity. And in 2018, Vafa and collaborators advanced a conjecture with a chilling implication. It proposes that no stable universe with a positive cosmological constant, no true de Sitter vacuum, exists anywhere in string theory at all, not in any valley, not among the 10 to the 500. If that conjecture is right, the elaborate landscape constructions that claim to build universes like ours, and they have been contested, technically, ever since they were published, do not actually work, and string theory does not merely lack a description of our world. It forbids our world. The conjecture is unproven, fiercely debated, and its supporters offer an escape hatch, that dark energy might not be a true constant, but a slowly decaying field, in which case our universe never quite becomes de sitter, and the theory survives on a technicality. Astronomers, as it happens, are testing whether dark energy evolves at this very moment. Hold that thought. We will need it again before the night ends. But for now, absorb the position the field has actually been standing in, beneath all the confidence of those decades. The only precise quantum gravity humanity possesses is formulated in a universe of the wrong shape. And Susskind's response, at 84, is the sentence a founder is never supposed to say, and the one he keeps saying anyway. We have to start over again. We have to start building theories that don't have boundaries, because de sitter space does not have a boundary. Start over, not renovate, not extend. And you would think, would you not, that after such a diagnosis from such a source, the brightest young minds in physics would be stampeding into the problem, the universe we live in, lacking its fundamental theory, virgin territory, glory on the table. You would think that. What is actually happening is the strangest part of tonight's story, and it is not about equations at all. But before we get to the people, we have to close one more door, the one marked. Maybe the experiments will save us, because you might still be hoping that some measurement, some machine, some clever observation will simply test the theory and settle all of this. That hope has a shape, and the shape is a wall. Science has a court of final appeal, and it is not a person. When theorists disagree, when arguments harden into camps, when a field's giants contradict one another with absolute confidence on all sides, the tradition of physics says, calm down and build the experiment. Nature will vote. Every crisis in the history of the subject was eventually settled this way. The ether was voted down by an interferometer. The quantum was voted in by glowing metal and stubborn spectral lines. So it is natural, hearing everything you have heard tonight, to assume the same referee will arrive here. Give it a decade, or 3. Build the machine. Ask the universe whether it is made of strings. And this is the chapter where I have to show you why that referee may never arrive, not because of money, not because of politics, but because of physics itself. String theory is not just hard to test. It sits behind a wall that may be woven into the laws of nature. Start with the numbers, because they are brutal and they are clarifying. A string, if strings exist, has a characteristic size near the Planck length, 10 to the minus 35 meters. The most powerful microscope humanity has ever built, in effect, is the Large Hadron Collider, which probes distances by colliding particles at enormous energies, because in quantum mechanics, seeing smaller requires hitting harder. The collider reaches about 10 to the minus 19 or 20 meters. Read those exponents side by side. The gap between our best instrument and the string scale is 15 to 16 orders of magnitude. That is the gap between the width of a human hair and the distance to the nearest stars. To probe the Planck length by the same methods, you would need collision energies about a quadrillion times beyond the colliders. And if you scaled today's technology to deliver them, the machine would not fit in a laboratory, or on the Earth, or in the solar system. It is a galaxy-sized apparatus for a question we wanted answered by Tuesday. And even patience does not save us, because Susskind points at something worse than expense. Suppose you could keep building bigger machines. Suppose energy were free. There is a trap waiting at the bottom of that road, and Susskind takes personal ownership of the argument. The interviewer attributed it to a younger famous physicist, and Susskind corrected him with visible amusement. It wasn't him who said that, he said. He is quoting me. Here is the trap. For all of modern physics, higher energy has meant finer resolution. The harder you hit, the smaller you see. That is the whole logic of the accelerator century. But concentrate too much energy into too small a region, and general relativity wakes up. The energy density curves space. Push to the Planck scale, and the curvature closes. Your probe does not resolve a smaller distance. It forms a black hole, and now the trap springs shut, because feed the collision even more energy, and the black hole does not sharpen your view. It grows. More energy, bigger hole, bigger horizon, coarser resolution. The road of higher energies, followed to its end, bends back on itself. Short lengths become long lengths again, Susskind says. In his view, this is not a limitation of our machines, but a limit in nature. The same character of limit as the uncertainty principle, which does not say we lack the tools to know a particle's position and speed at once, but that the world contains no such fact to know. Below the Planck length, there may be nothing to see, not because our eyes are weak, but because distance itself dissolves as a concept. The wall is not in front of the door. The wall is where the door was supposed to be. So direct tests are closed, and the field has known it forever. The honest hopes were always indirect, footprints rather than sightings, and it is worth an honest accounting of them. Supersymmetric partner particles at accessible energies were the great hope. The collider has answered with a decade and a half of silence, as we saw. Extra dimensions large enough to modify gravity at small distances. Torsion balance experiments have measured gravity's inverse square law down below the width of a human hair and found no deviation. Cosmic strings stretched across the sky. Primordial gravitational wave patterns imprinted by string-scale physics in the universe's first instant. Subtle correlations in the afterglow of the Big Bang. Each of these remains possible in principle. Each has so far returned nothing decisive. After 58 years, the count of confirmed, string-specific experimental predictions stands at 0. That is not a rhetorical 0. It is the actual number. And here the strange little fact from the beginning of tonight comes back, the one I asked you to file away, because it is the cleanest single measure of the situation that exists. Consider the prizes. The Fields Medal is the highest honor in mathematics. Edward Witten won it in 1990, the first physicist ever to do so, for insights that flowed out of string theory into pure mathematics. And string-theoretic ideas have fed Fields-level mathematics repeatedly since. The Nobel Prize in Physics, by tradition and by rule, rewards work confirmed by experiment or observation. In 58 years, string theory has produced Nobel Prizes for exactly no one. Susskind said it in the interview as a plain fact. No physicist has ever won a big prize for string theory. The prizes are a ledger, and the ledger says, this body of ideas has been certified true in the world of mathematics, and never once in the world of things. Mathematicians won medals for it. Physicists are still waiting to find out whether it is physics. Now, precisely because the situation is this stark, some critics reach for a heavy word. Unfalsifiable. Not science at all, they say, since no possible observation could refute it. If a theory can hide forever behind an untouchable wall, has it not stopped being physics? Susskind has heard that word for decades, and in the interview, he pushed back with history and with proposals, and both halves deserve your attention. The history first. When Greek thinkers proposed atoms 24 centuries ago, the objection was exactly this one. Too small, no possible eye will see them, unverifiable forever, and it held, in fairness, for a very long time, and then technology arrived, where philosophy had been, and atoms were counted, weighed, and photographed. When quarks were proposed in the 1960s, the same objection came. Confinement guarantees no one will ever see a free quark, and yet the indirect evidence, jets and scaling patterns in collisions, became so overwhelming that no one doubts quarks today. What is unverifiable at one time, Susskind said, becomes verifiable when technology improves. Something can be unverifiable within current technology and still be true. And then, to his credit, he named observations that could actually bear on the picture, not on strings directly, but on the landscape cosmology attached to them. And the first one may surprise you, after everything I have said about walls. The bubble universe picture, universes nucleating inside eternal inflation, makes a statistical prediction about the overall shape of space in any given bubble, including ours. Bubbles born that way inherit a slight negative spatial curvature, an overall openness to the geometry of space itself. So measure the universe's global curvature. Right now, observations of the cosmic afterglow say space is flat to about 1 part in 1,000, consistent with a tiny curvature either way. If future surveys sharpen that measurement and find a small negative curvature, the landscape picture gains a point, not proof, but a point. And if they find positive curvature, a closed, sphere-like geometry, then, Susskind says flatly, that would be a direct refutation. The picture would be wrong, and he says so in advance, which is precisely what a falsifiable claim sounds like. He adds a second signature, stranger still. If other bubbles ever collided with ours in the distant past, the bruise would survive as a faint circular scar in the cosmic microwave background, the baby picture of the universe. People have looked. Nothing conclusive has been found. But it is a real signature, in real data, and the looking continues. So the honest verdict on the wall is layered, and I will not flatten it in either direction. The core of string theory, the strings themselves, the Planck scale structure, sits behind a barrier that may be physically absolute, and the theory's characteristic predictions have gone 58 years without a single confirmation. That is the hard half. The other half is that the theory's cosmological consequences leak out into measurable sky, curvature, scars, the behavior of dark energy, and that the history of physics is a long record of unverifiable things becoming verifiable on timescales no one predicted. Both halves are true. What you cannot honestly say is that the referee is on the way. For the deciding questions, there is no experiment scheduled, no machine on any drawing board, no vote from nature pending. This crisis will not be settled from outside. Whatever rescue comes must come from within, from human judgment, human imagination, and human courage. Which brings us, finally, to the humans. Because a field that cannot be corrected by experiment is a field held up entirely by the quality of its people, their honesty, their willingness to wander, their tolerance for risk. And it is exactly here, Susskind says, at the field's only remaining load-bearing pillar, that the deepest damage has occurred. Not in the equations, in the culture, in the young. Something happened, during those decades of conquest, to the kind of courage that physics runs on. And when the old man in the interview talks about it, all the amusement leaves his voice. Every crisis we have walked through tonight has been made of mathematics. This one is made of people. And I will tell you now, before we begin it, that this is the chapter Susskind himself seems to care about most. The one where the 84-year-old physicist stops describing equations and starts describing his students, and the room they will not enter. Recall where the physics left us. The universe we live in, de sitter space, positively accelerating, wrapped in horizons, has no precise quantum theory. Not from string theory, not from anywhere. Susskind calls the problem the thing he has been circling for 30 years, and in a focused way for the last 5. So the interviewer asked him the natural question, the one you are probably asking. If this is the fundamental theory of the actual universe, sitting unsolved, the biggest open problem in the deepest science, why isn't everybody working on it? Listen to the answer, from the ultimate insider, a man who has spent 50 years at the center of the field's most powerful institutions. Beats me, he said. I don't know. You'll have to ask them. But he did not leave it there, because he has asked them. He described what happens when he puts the problem in front of young physicists, the brilliant 20-somethings passing through Stanford, one of the 2 or 3 most rarefied physics environments on Earth. When I ask young people, he said, they say it's too hard. And I say, come on, it's virgin territory. Anything that you manage to say about it will be new. Thinking about old things is very hard, because almost everything has been said by somebody in the past. This is open territory. Just get into it. Hear what he is offering them. In science, the scarcest resource is not talent and not funding. It is untouched ground. Questions where no thicket of prior literature stands between you and discovery. Susskind is standing at the edge of the largest patch of untouched ground in physics, the quantum theory of the actual universe, waving the next generation in. And then comes his report of their answer, and it is the saddest sentence of the night. And they say, no. They're scared. They're scared they might not get a job. He does not mock them for it, and neither should we, because they are not wrong. Understand the machine. A young theoretical physicist lives inside. A doctorate takes 5 or 6 years. Then come the postdoctoral years. 2 positions, sometimes 3, each 2 or 3 years long, each in a new city, often on a new continent, at salaries that would make a software intern wince. A decade of maximum effort, and at the end of it, a number. The number of permanent faculty positions in fundamental theory in a good year across the entire United States is a few dozen. The number of qualified applicants is hundreds. Every hiring committee that meets will compare candidates by their publication records, their citation counts, their letters from famous names. Now put yourself in the shoes of a 26-year-old deciding what to work on. Path 1. Join an established program, where the problems are well defined, the seniors are productive, papers come steadily, citations accumulate, and every committee member recognizes the work. Path 2. Walk into Susskind's virgin territory, where the problem is so hard that he himself, one of the great physicists alive, has circled it for 30 years without cracking it, where you might publish nothing for 5 years, and where, when your file lands on the committee's table, it will show a handful of strange papers on a question most of the field politely avoids. They might be right, Susskind conceded, about the job. And then he said what the logic of a career can never quite contain. That's not the criteria for whether you should work on something in science. You should work on it because you're curious. You should work on it because it's relevant to the real world. And not, in my view, be afraid. Here is the bitter historical irony, and tonight you have everything you need to taste it. Go back to part 3. String theory itself was born from exactly the kind of recklessness that today's incentives punish. When the field abandoned strings in 1974, John Schwartz kept working on them for a decade, in unfashionable near solitude, and that stubbornness is the only reason the 1984 revolution had anything to revolve around. Every pillar of this story, Veneziano chasing a 200-year-old formula, 3 physicists seeing strings where everyone else saw points, Shirk and Schwartz declaring their dead hadron theory, a theory of gravity, every one was a career gamble taken against the consensus of its moment. String theory conquered physics, and the conquest built a monoculture. And the monoculture now structurally deters the very species of gamble that created string theory. The tree grew so large it shades out its own seedlings. And there is a second symptom of the crisis, subtler than fear, and in its way more corrosive, and tonight it needs to be said plainly. The field has begun to lose its grip on what its own theory is. At the annual flagship conference of the discipline, the world's leading string theorists were asked, on stage, in a formal session, a question that sounds like a joke. What is string theory? And there was no uniform answer. Some define it as the perturbative theory of vibrating strings. Some as M theory, whatever M theory turns out to be. Some as the boundary correspondence itself. Some, in effect, as whatever consistent quantum gravity eventually emerges from this circle of mathematics. The theory that organized 40 years of physics does not currently possess an agreed definition among its own leaders. You have watched Susskind himself navigate this all night, and now you can name what he is doing. When he says string theory is certainly not the real world, he means the precise supersymmetric structure, and he calls it string theory with a capital S. When he expresses hope, it attaches to a generalization that does not yet exist. A lowercase string theory, some expanded, less supersymmetric, more flexible descendant, and the hope is that the name will stretch to cover whatever is eventually found. The word string theory has become a bridge between a mathematics that is exact but not real, and a dream that is real, but not yet mathematics. The theory's critics, and it has fierce, credentialed, persistent critics, have savaged this ambiguity for years. Their argument goes like this. A research program promised the world a unique theory of everything. What it delivered is a framework that fails to describe our universe in its precise form, and survives by continually redefining success, so that every achievement counts for string theory, while no failure ever counts against it. One commentator built the mockery into a parable. Imagine a company that promised flying cars, failed to build one, and then announced that it was no longer a flying car company with a capital F. It was a successful flying car company with a lowercase f, having redefined flying as any moment both wheels leave the road on a bump. The cruelty of the parable is not the point. The point is the question underneath it, and it is a fair one. At what moment does redefining the goal stop being intellectual flexibility and start being an inability to say the word wrong? The critics add a darker count to the indictment, that the monoculture did not merely outcompete alternatives, but starved them. That for 2 decades, a young physicist working on rivals to string theory could not get hired at a leading department, and that the field enforced its consensus not by refutation, but by hiring committee. That charge is bitter, contested, and impossible to fully adjudicate. What can no longer be denied, after the interview at the center of tonight, is its kernel. When the founder himself reports that the young are too scared to work on the actual universe, the debate about whether the incentives are broken is, quietly, over. The incentives are broken. The remaining argument is only about how it happened and who pays. Now, because this is a story about physics and not a courtroom, let me give the last word of the chapter to the strange, luminous contradiction that Susskind embodies, because I think it holds more truth than either side's clean version. In the very same interview, this man defended scientific consensus with real force. Don't look for the weirdos, he said, when asked how outsiders should judge competing claims. Think about the consensus of the largest fraction of accomplished physicists, and you'll probably be right. Peculiar individuals, no matter how famous, no matter how brilliant, off the consensus for a long time, are probably wrong. He believes that. His whole career testifies that consensus science mostly works. And the same man, asked at the end of the interview what advice he would give the young, said this: "The primary thing I would tell people is, don't listen to old people." He told the story of students who brought him ideas, whom he waved off, and who abandoned those ideas just before they became important. I was wrong, he said. They listened to me, and they lost the opportunity to do something very impactful. Follow your curiosity, he said, even if it points away from everything your elders are doing. And if you don't think you can do that, you're probably in the wrong field. Trust the consensus. Don't listen to the old. Both, from one man, in 1 hour, and he sees the tension and lets it stand, because the tension is the actual, unresolved truth of how science works. The consensus is almost always right, and every revolution comes from someone who ignored it, and there is no rule, none, for telling in advance which moment you are living in. Except that sometimes the consensus itself starts telling you. That is what makes this moment in physics so strange, and so unlike the textbook cases. The warning is not coming from the weirdos this time. It is coming from the throne. And that raises the question this chapter has been circling all along, the one the young physicists ask themselves at night, and the one you should now be asking too. If they did find the courage, if some brilliant 26-year-old walked away from the safe path tomorrow, ready to start over, where exactly would she go? What is the alternative? What else is on the table? The answer to that question is the emptiest room in physics, and we should go look at it. In sports, when the star player goes down, everyone's eyes turn to the bench. Physics works the same way. If string theory is injured, and by now you know precisely how injured, Then surely somewhere on the bench sits the replacement. A rival theory warming up, waiting for its minutes. The interviewer put exactly this to Susskind, straightforwardly. What other approaches exist that reconcile general relativity with the standard model of particle physics? And Susskind's reply is one you should hear in full, because it may be the most quietly devastating passage in the entire conversation. There is none, he said. There are none. There simply are none. If there was one, we'd be working on it. That's the problem. Let me make sure the shape of that answer is clear, because it reframes everything the critics say. The accusation against string theory has long been that it monopolized physics, crowding out worthy alternatives. And there is truth in the sociology of that, as we saw. But Susskind's point cuts underneath it. The alternatives that exist do not do the job. The job, remember, is double. Contain quantum mechanics and gravity together, and connect to the actual particles of our world, the electrons and quarks and photons of the standard model. String theory, for all three of its cracks, does the first half exactly, in the wrong kind of world, and gestures at the second. Nothing else on the bench, in Susskind's assessment, completes even that much. Still, honesty requires us to walk the bench and look at who is sitting on it, because several programs deserve their names spoken and their ideas taken seriously, and the fate of each one teaches something. The most substantial is loop quantum gravity, the leading rival for 4 decades. Where string theory begins with particles and fields and tries to grow gravity, loop quantum gravity begins with Einstein's geometry and tries to quantize it directly. No strings, no extra dimensions, no supersymmetry required. It paints an austere and beautiful picture. Space itself, at the Planck scale, is not smooth but woven, a network of discrete loops and nodes, with area and volume coming in smallest possible pieces, atoms of geometry. Time advances as the network rewires. The theory has real achievements, a discrete spectrum for areas and volumes, its own account of black hole entropy, and applications to the Big Bang in which the singularity is replaced by a bounce. Susskind, asked about it, was more generous than his reputation might suggest. Better motivated, he called it, based on ideas that at one time he found interesting, and he added something few people at his altitude ever say. He studied it, years ago, seriously, and his verdict, delivered without heat, was that it seems to be petering out, not refuted so much as stalled, unable, so far, to demonstrate that its woven space heals into the smooth space-time of Einstein at large distances, and unable to reach out and touch the standard model. Then he opened a door most string theorists keep firmly shut. I wouldn't be totally surprised, he said, if some features of string theory turn out to be consistent with some ideas from loop gravity. That could change, he said, of the stall. It is worth pausing on the humility of that. The dean of string theory, allowing that the rival church might hold a piece of the truth. Further down the bench sit the independents, the physicists, some deeply credentialed, some self-taught, who have each proposed their own theories of everything, and whose names circulate endlessly online, attached to claims that the establishment is suppressing the answer. The interviewer, to his credit, named several and made Susskind respond, and the exchange is a lesson in how a serious physicist actually evaluates ideas. So let me give you its texture honestly, including its bluntness. One proposal builds the universe from cellular automata, simple computational rules iterated endlessly, updated in recent years into a framework of evolving hypergraphs. Susskind's response was a single clean cut. That certainly doesn't contain either gravity or quantum mechanics, he said, so it's a failure. Whatever its philosophical interest, until a computational model demonstrably produces Einstein's equations and quantum interference, it is not yet a competitor in this arena. Another physicist critic, famous for the position that string theory is not even wrong, meaning it fails to make testable claims at all, has his own unification proposal. Susskind, asked about it, went and read the papers, and reported, With a candor he immediately flagged, as perhaps improper, that he found them bad mathematics and bad physics, with nothing to offer, adding, "I probably shouldn't say that, but I'm going to say it anyway." Another independent builds particles and forces into the largest of the exceptional symmetry structures in mathematics, a proposal of undeniable elegance whose difficulties with the three families of matter and with gravity itself have been documented at length. "I can't understand what he's doing," Susskind said, simply. And then, having delivered all these verdicts, this 84-year-old did something that almost never happens in these arguments, on any side. He took it back. Not the assessments, but the certainty. "You have to dismiss what I say about these people," he told the interviewer, "because I have not studied what they said in detail. It is possible that somebody offbeat is thinking something much deeper and smarter than I think. Maybe it's one of these people. I don't know." And then came the sentence that, given everything else in this story, should be printed on the wall of every physics department on Earth. We should certainly be on the lookout for ideas which are not the consensus. We should be watching for them, and not immediately dismiss them because they're not exactly the same as the ideas we've been pursuing. And maybe, he added, we haven't been diligent enough with some of these ideas. From the man who, an hour earlier, had advised trusting the consensus and ignoring the weirdos. The contradiction from the last chapter, standing in the open again, unresolved, because it is unresolvable, and he is too honest to pretend otherwise. So here is the true inventory of the bench, and it is the bleakest fact of the night so far. The reigning theory describes, with certainty, per its own founder, the wrong kind of world. The leading rival is, in his judgment, petering out. The independents have not, in his judgment, produced a theory that contains gravity and quantum mechanics at all. And the honest ones, on every side of every one of these disputes, agree on exactly one thing, which Susskind said out loud, and which almost no one in his position ever says. Criticizing without offering better is easy, he acknowledged, and, speaking of his own dismissals of the many worlds pictures and the deterministic heresies of his old friend Hooft, he said, "I don't have anything to offer which is any better. It's almost useless for me to say I'm skeptical. There is no secret replacement. There is no suppressed rival waiting in a drawer. The bench is empty, and everyone senior enough to see the whole field knows the bench is empty. If your stomach dropped slightly just now, hold that feeling, because it is the correct response, and it is also, strangely, not the end of the story. An empty bench does not mean an empty future. It means the future will not arrive by substitution, one finished theory swapped for another. It will have to be built from parts, and this is where the story turns, because the parts exist. Out of string theory's wreckage, over the past decade and a half, a set of ideas has been quietly salvaged, ideas strange enough that they may not belong to string theory at all, but to whatever comes after it. Entanglement stitching space together, wormholes, identical to quantum correlations. The interiors of black holes growing like a computation, and an old man in California, ignoring his own advice about consensus, spending his 85th year building toy models of the universe's expansion. Alone, out on the virgin territory, he cannot convince anyone else to enter. The last stretch of our journey is about what survives, and it begins with the strangest coincidence in the history of physics. 2 papers, written by the same man, in the same year, 1935, that waited 80 years to be recognized as the same paper. In 1935, Albert Einstein, working at Princeton in the long twilight of his career, published 2 papers. He wrote them with different collaborators on what he believed were different subjects, and for 80 years, the world agreed that they had nothing to do with each other. The first paper, written with Nathan Rosen, was about geometry. Studying the mathematics of black holes, Einstein and Rosen found that the equations of general relativity permit a strange structure, a tunnel, a throat of curved spacetime connecting 2 distant black holes, so that the two far apart openings are, through the tunnel, adjacent. The structure became known as the Einstein-Rosen bridge. Today we call it a wormhole. It was a curiosity of pure geometry, gravity's strangest doodle. The second paper, written with Boris Podolsky and Nathan Rosen, was about quantum mechanics, and it was intended as an attack. Einstein had never accepted the quantum theory's spookiness, and this paper aimed at its strangest implication, that two particles, once they have interacted, remain correlated no matter how far apart they travel, so that measuring one instantly shapes what can be found about the other, across any distance, a connection stronger than any classical theory allows. Einstein meant the paper to expose this entanglement, as it came to be called, as evidence the theory was incomplete. Instead, he had put his finger, more precisely than anyone before him, on the deepest feature quantum mechanics has. Entanglement is real. It has been confirmed in the laboratory beyond all doubt, and the experiments confirming it earned the Nobel Prize in 2022. Two papers, same man, same year. One about tunnels in space-time, one about connections between particles. Nothing to do with each other. And then, in 2013, 78 years later, Juan Maldacena, the same Maldacena of the correspondence, and Leonard Susskind, the man whose voice has carried this whole night, proposed something that sounds less like physics than like poetry. The two papers were about the same thing. Their conjecture is written as an equation of initials, ER equals EPR. Einstein and Rosen's bridges are Einstein, Podolsky, and Rosen's entanglement. When two black holes are quantum mechanically entangled, Susskind explained in the interview, they are connected by an Einstein-Rosen bridge. Wormholes and entanglement, he said, are the same thing. Einstein, Susskind suspects, never saw it. I think it was accidental that they both occurred the same year, he said. The old man had drawn the same secret twice, from two different sides of the paper, and died without knowing. Now let me take you inside what this means, because it is the doorway to the biggest idea left standing in fundamental physics. Picture two black holes, far apart in space, a light year between them. Now suppose that they were created together, in such a way that every quantum degree of freedom of one is entangled with a partner degree of freedom in the other, a perfect pairing across the dark. Each hole, examined alone, looks utterly ordinary, a featureless sphere of no return. Nothing passes between them. No signal, no force, no influence. And yet, according to ER equals EPR, the geometry of space-time itself registers their relationship. Behind the two horizons, the two interiors are joined, one shared room with two entrances, a bridge made of nothing but correlation. You cannot use it to travel or to send a message. The mathematics forbids it with perfect consistency, but it is there, in the shape of space. And now run the logic in the direction that matters. If enough entanglement between two systems is a wormhole, then perhaps a little entanglement is a little geometry. Perhaps every pair of entangled particles, the ones physicists make by the millions in laboratories, is joined by some quantum thread of connectedness, far too fine to call a tunnel, and perhaps this is the idea, the smooth continuous space you live in, the sheer connectedness of here to there, the fact that the universe is one room and not a spray of disconnected points, is itself made of entanglement. Stitch by stitch, thread by thread, quantum correlation is what sews the world together. Cut all the entanglement between two regions, calculations suggest, and space between them would literally fall apart, tear like a fabric into separated pieces. Space is not the stage on which quantum mechanics performs. Space is a pattern that quantum mechanics weaves. Susskind added a second thread to this picture, and characteristically, it came from thinking about what black holes do after everyone else stops watching. A black hole settles down very quickly. Feed one, disturb one, merge two, and within milliseconds, For a hole the mass of the sun, the horizon smooths itself, and the object reaches what physics calls thermal equilibrium, its temperature steady, its entropy at maximum, all measurable excitement over. From the outside, the story is finished in under a second. But Einstein's equations say something is still happening inside. The interior volume of the hole, the room behind the horizon, keeps growing and growing, long after the outside has gone still. For time beyond time, exponentially long, the inside gets bigger. For decades this was a curiosity nobody could interpret. What property of a physical system keeps increasing long after its entropy has topped out and its temperature has settled? Nothing in the classical toolbox behaves that way. Susskind found the answer in a place physicists had never looked: the theory of computation. There is a quantity computer scientists call complexity, the minimum number of elementary operations, simple steps, gates in a quantum computer, needed to build a system's current state from a simple starting point. Entropy measures how scrambled a system is, and scrambling saturates fast. Complexity measures how intricate the scrambling's history is, how long the shortest recipe for the present state has become, and in quantum mechanics, complexity keeps climbing for almost unimaginable spans of time after entropy has flatlined, a fact Richard Feynman had sensed decades earlier when he mused about why quantum systems are so hard to simulate. Susskind's proposal, complexity equals volume. The growing interior of the black hole is the growth of quantum computational complexity, made visible as geometry. The inside of a black hole is, in a sense that may be perfectly literal, an ongoing computation, and its size is the length of the program so far. When he proposed it, he said in the interview, he knew of essentially two physicists in the world who understood what computational complexity even was: his Stanford colleague Patrick Hayden and his own former student Daniel Harlow. Now, he said, everybody working on quantum gravity knows it, probably better than I do. Step back and look at what these salvaged ideas have in common, because this is the quiet revolution that survived the crisis. Entanglement is geometry. Complexity is volume. Entropy, as Susskind put it in the interview in his beautifully plain way, is hidden information, the count of everything true about a system that is too fine, too numerous, or too far behind a horizon for you to access. Every one of these is a statement of the same creed. Space-time is not fundamental. Information is. The bending of space, the growth of interiors, perhaps the existence of distance itself, are the outward appearance of quantum information doing what quantum information does. This creed grew up inside string theory. Its proofs and checks live in Maldaceno's boundary world, in the wrong kind of universe, as ever. But notice, and this is what makes it the seed of whatever comes next, the creed itself never mentions strings. It speaks only of entanglement, information, complexity, horizon, things any quantum universe possesses, including, presumably, ours. The tools have quietly detached themselves from the theory that forged them. If the theory of our world, of de Sitter space, is ever built, most physicists now suspect it will be built from these. And that is exactly what the old man is trying to do. At 84, with his deadlines and his 30-year obsession, Susskind is not writing string theory papers. He described it in the interview with the modesty of a man who has learned what confidence costs. I've been experimenting around for a number of years, he said, with a simple model, trying to argue that it describes some kind of de Sitter space, a toy universe, a small, exactly solvable quantum system, a laboratory of pure mathematics, in which he believes he can see the fingerprints of exponential expansion, the thermal breath of a cosmic horizon, the signature behaviors of a world like ours, rising out of nothing but entangled quantum parts. Is he right? Listen to how he answers, this man who once told you he could speak with absolute certainty. I'm not sure my colleagues agree with me, he said. And then, the bottom line is, we know very, very little about it. The most senior figure in the field, out on the furthest limb, holding a handmade model of the universe, telling you plainly that he does not know. Whatever else the crisis has cost, it has not cost him that. The willingness to be unsure, out loud, at the very end of a career, built on being right. So the salvage is real. The tools survive. The creed survives. One founder is still building. Which means we can finally do what the beginning of tonight promised. We can add it all up. The dream, the accident, the conquest, the triumphs, the 3 cracks, the wall, the fear, the empty bench, the salvaged threads. It is time to answer the question in the title. There is a crisis in string theory. Here is why it is worse than you think, and why that is not the end of the story, but the beginning of a different one. At the beginning of tonight, I made you a promise. I said that by the end, you would know exactly why the crisis in string theory is worse than you think. The night is nearly over. The pieces are all on the table. So let us keep the promise, plainly, and count. If you came into tonight having heard the critics, you probably thought the crisis was this. String theory might be wrong. And if that were the crisis, it would not be a crisis at all. Theories are wrong all the time. Being wrong is how physics breathes. The ether was wrong, and its wrongness gave us relativity. The steady-state universe was wrong, and its wrongness gave us the Big Bang. If string theory were simply wrong, some experiment would show it, some rival would replace it, and the field would mourn for a season and move on stronger. That is the ordinary life cycle of ideas, and nothing about it deserves the word crisis. The actual situation is not ordinary, and here is its full shape, assembled from everything you now understand. The only mathematically precise theory of quantum gravity the human race possesses is not wrong. It is worse than wrong. It is exactly, provably, spectacularly right about a universe that is not this one. It requires a symmetry, supersymmetry, that our world has been searched for and does not have, and no version of the theory without that symmetry exists, not because no one tried, but because everyone tried, for 50 years, including the man who told you tonight, I worked on it, and I failed. It offers, in place of one universe, at least 10 to the 500, so many that it can no longer forbid anything, and a theory that forbids nothing predicts nothing, and beneath both of those cracks lies the deepest one. Every exact result the theory has ever proven lives in anti-de Sitter space, the bowl-shaped world with a wall at infinity for the hologram to hang on. And in 1998, we measured which world we live in, and it is the other one, the running world, the world wrapped in horizons instead of walls. The wrong kind of world, in Susskind's phrase, except, and this is the correction the whole night has been building toward, the world is not wrong. The world is the only thing that cannot be wrong. The theory is aimed at the wrong world. Our equations are written on a wall the universe does not have. That alone would justify the title. But now add the second layer, the one that turns a hard problem into a genuine crisis. There is no referee coming. The strings themselves live behind the plank wall, 15 orders of magnitude beyond our finest instrument, and past that wall, more energy makes black holes, not resolution. The court of experiment, which settled every great crisis in the history of physics, has no jurisdiction here, not this decade, possibly not ever, and there is no bench. You heard the founder himself take inventory. Alternatives that reconcile gravity with the particles of our world. There are none, he said. There simply are none. If there was one, we'd be working on it. And now add the final layer, the human one. The people who must build the replacement, the young, the brilliant, the ones with decades ahead of them, are not building it. They stand at the edge of the largest patch of virgin territory in science, the quantum theory of the actual universe. And they do not go in, because the field that raised them punishes wandering, and they are scared they might not get a job. The theory cannot describe our universe. The experiments cannot reach it. The alternatives do not exist, and the rescue party is afraid to leave the building. That is the crisis. It is not that string theory failed. It is that string theory succeeded at everything except the universe, and the structures we built around its success are now the very things preventing the next attempt. Worse than you think, exactly as promised. And yet, you have listened this far, and you know this channel never ends a story at its darkest sentence, because the darkest sentence is almost never the truest one. So now let me show you the same facts from the other side, because there is another way to read this whole night, and I believe it is the more honest reading. Every era of physics that we now call golden looked, from the inside, exactly like this. The 1890s, when the great minds announced physics was nearly finished, just before radioactivity, the electron, the quantum, and relativity detonated everything, were not a golden age to the people inside them. They were a fog of small anomalies nobody wanted, black body curves that would not fit, an ether that would not appear. The 1920s, the most creative decade physics ever had, was lived as a crisis, a panic of failing models and broken pictures, until the panic acquired a name: quantum mechanics. A crisis in fundamental physics is not the field dying, it is the field molting. It is the sound an old skin makes when what is inside has grown too large for it. The scandal of our era, remember, is not that we know too little, it is that we know too much that does not fit. We hold an exact quantum gravity for the wrong universe, an exact particle physics with no gravity in it, a cosmos measured to exquisite precision and made of ingredients we cannot name. That is not poverty, that is a hoard of clues, the richest inheritance any generation of physicists has ever been handed. And the clues have a direction. You watched it assemble tonight. Space-time is not fundamental, information is. Entanglement builds geometry. Complexity builds interiors. Horizons keep accounts. Those ideas were forged inside string theory, checked inside the bowl-shaped world, and every one of them has now slipped its leash and speaks about any quantum world, including, presumably, the one outside your window. Somewhere in that direction, most physicists now quietly believe, lies the theory of our universe, the one that does for the horizon what Maldacena did for the wall. It does not exist yet. Nobody knows its shape. Susskind's little models are one man's flashlight, sweeping the edge of it. What the problem is waiting for, by his own testimony, is not a machine, and not a genius, exactly. It takes not only great brilliance, he said, it takes some courage. There is that word again, the one I asked you to carry all night, next to the wrong kind of world. 50 years ago, string theory was born because a handful of stubborn people worked on something dead, unfashionable, and too hard for no reward the world could see. That is the only way anything in this story was ever born. The next theory is presently sitting where string theory sat in 1973, unwritten, unstaffed, and waiting for someone too curious to be sensible. Anything you manage to say about it will be new. Somewhere, maybe not yet in graduate school, maybe not yet born, is the person who will not listen to old people, exactly as the old man begged. And here is the last thought I will leave you with, the one to hold as you drift. Tonight you learned that we live in the wrong kind of world, a universe of horizons, running away from itself, with no wall at infinity to write its description on. But lie still for a moment, in the dark, inside that fact. The wrongness was never in the world works perfectly. Every atom of you is being held together, right now, by quantum mechanics and gravity, in flawless, effortless cooperation. At the center of every black hole the reconciliation is already accomplished, and space is being woven, thread by entangled thread, out beyond the last galaxy you will ever see, without the slightest need of our permission or our comprehension. The universe is not in crisis. The universe has never once been in crisis. The crisis is only in our description of it, and descriptions are things that human beings, some of them young, some of them frightened, some of them lying awake at this very hour, get to rewrite. The book of nature is not closing. It is sitting open at a blank page, the way it was for Newton, the way it was for Einstein, the way it is tonight, for whoever finds the courage. We were wrong about the shape of the answer. We were never wrong to ask. Thank you for spending this night with me, walking the length of physics' strangest confession, from a vibrating string in an old formula to the horizon at the edge of everything. If explorations like this one are how you like to end your day, a quiet like or subscribe would mean a great deal. It truly does help me keep making these long journeys through the deepest questions we have. And remember, the next time you drop something, a key, a coin, a book from a tired hand, that in that small fall you are watching gravity and the quantum world cooperate in a way no equation on Earth can yet describe, and that somebody, someday, will finally write it down. Good night, and may you never look at an unanswered question the same way again.